All right, guys. This is the second part of our biomechanics lecture. If you remember, last time we ended on data conditioning. Then we dedicated an entire class period to going over the conditioning that you would need to do in the Excel spreadsheet to get your data ready, and then to run the program, um, Dr. Fogelman's macros and VBA program for your biomechanical analysis and the reports that you're going to be putting together. What we talk about today will be relevant for your the take-home portion of exam one, where you'll be doing a static biomechanical analysis. Now, I will uh, walk through this with you in class, just because I feel like a recorded lecture won't do it justice. It'll be important for us to do one together, so you have a general sense of how to do it. But this is where we get to use that lovely trigonometry that we reviewed earlier, about a week ago, week and a half. So modeling static forces uses it looks at external and internal static forces. And if you recall, static means that there's no motion. And so if you look at the sum of all the forces acting on something, it would be zero if it's not moving. Okay, so if I have a 5 pound weight in my hand and I'm holding it still in the air, that means that gravity is pulling down with a force equal to its acceleration and the 5 pounds, but my arm is pushing up with an equal force just in the opposite direction. So basically, it's canceling out gravity, and so there's no motion. External static forces use available. It's available from motion measurement data and looks at reactive and resultant forces and moments. For internal static forces, we have to make inferences about forces exerted by the muscles acting upon bone, and we'll talk more about that. All right, you can see here on the right, we've got a forearm holding a weight. If this is, like I was just mentioning, if this is static, you can see, looking over at the top left here of the notes, the sum of the forces external equals zero, at least in the y direction. So when we look at the weight of the load and the weight of the forearm and the hand plus the reactive forces, it equals zero. Okay, and because we know what the load is, and we can calculate the weight of the forearm and the hand, then we can estimate what that reactive force is at 64.8 newtons. And we'll talk about how we get that in just a minute. It's exciting. I'm sure you guys will love it. um, and the same with the moments. So you can see the sum of all the moments are zero, and that is think of it as like torque rotational force. So here we have the um, the distance and the weight of the load. That's how we get a torque. It's the distance away from our fulcrum. If you look at the elbow here, it's got this little arrow and then a little circle and a dot. So that's the fulcrum that we're talking about. The further away our load is from that fulcrum, the greater the torque is going to be. Um, and so you can see the distance of the load times the weight of the load gives a torque, minus the distance of the forearm and hand times the weight of the forearm and hand. And you might ask, how do we know the weight of our forearm and hand without chopping it off and weighing it? This is going to be a morbid lecture, but we'll talk about that. And then the moment of external forces. So all of those put together should equal zero. If this is static and it's not moving, all of them added together should be zero. So in the same way, again, we can estimate the moments for those external forces, and here we get 20.1 Newton meters. All right, so now for that morbid part. So, well, not all of it, not all of it is so morbid, but generally, if you think of your height, and I'm going to use the height of a kid just to make the numbers easy. But let's say we're talking about 100 centimeters, so it's about a little over 3 foot. If if you were three, if you were 100 centimeters tall, the distance from the center of your shoulder joint to the center of your elbow would be 18.6 centimeters. So I don't know if this was anatomists or doctors, or not sure who did all the work to figure this out. Maybe it was ergonomists. I'm not totally sure, but anyway, someone has done a lot of measurements comparing your height, heights of the human body to the lengths of each of these segments, and they found out that um, the distance of your upper arm, the length of your upper arm is about 18.5% of your total height. Obviously, this is on average. There's some people I'm sure you've seen who have a huge torso and like little tiny short legs. I mean, I think of Kronk on Emperor's New Groove. Um, Shoulders like Kronk again, tree trunk, shoulders and biceps and then tiny little legs. There are exceptions, but on average, your forearm is about 14.6% of the length of the length of your total height, and then the length of your hand is about 10% of your total height. So that's how they came up with these numbers. And that's not so morbid, but we'll talk about the mass in just a minute. So you can see this figure breaks down all these different heights or segment lengths. You even have from your hip all the way down, from your knee all the way down, from your ankle down. So you can think, well, what if I needed the knee to the ankle? Well, you're gonna have to subtract 0.039 out of 0.285. So you get the idea. What we are going to be interested in for your assignment, particularly, are these numbers up here for the upper limb, for your arm. Now, so for the segment weights. Sorry about that. Recording while kids are asleep. So for the, let me get back here. To somebody chopped up cadavers and measured the center of mass for forearms, for upper arms, for the arm altogether, for just people's hands. Um, you know, I'm sure that was an interesting job. But anyway, so somebody has chopped up enough cadavers to find a good average estimate of the center of mass for all these body parts. So you can see here we have we have the upper arm, and we can see where the center of mass is in relation to the rest of the arm, for example. So you see here it says proximal and distal. So that means it's 43 from the proximal side. So if you remember what proximal versus distal means, proximal means it's closer, more proximate to your center, your body center. So if you go 43% of the way down from the proximal side, you'll hit the center of mass. If you're coming from so this is the upper arm. So if you're coming from the elbow and going up towards the core, then you'd have to go 56% of the length of the upper arm to get to the center of mass. So this tells us where that center of mass is. And then this other number, sorry, I don't know why I'm not full screen here. This other number tells us what percentage the upper arm, again, on average, I'm thinking of Kronk from Emperor's New Groove, his upper arm would not be just 2.8% of his body weight. It might be more like 5%, and his legs would be, a smaller percent than the average. But anyway, so on average, your upper arm is about 2.8% of your total body weight, which is interesting. So that is just to explain how this works. And again, these are all the numbers that we'll be interested in for you, the take-home portion of your exam for a static biomechanical analysis, particularly the forearm and the hand. We're just dealing with the wrist and the elbow joints. So, but that gives you an idea of how these work. So this is a single frame. You guys are familiar with the look of this frame because you have your own data for your own frames and with the joints that we've been referring to. And again, this is static, so no movement. So this is assuming you're holding this position, and you could imagine a box, weights out here. Sorry, I just want to be sure something here. All right, we're good. So you can imagine a weight, a box, something here that this person is holding, and these are simply the positions of these joints in space. Now this is where, no trig yet. Sorry, we're gonna get to that in just a minute. But here we're thinking of a person who's 168 centimeters tall. I don't know what that is in inches, but it's probably around 5'6", maybe, maybe a little taller. So if we want to know how long, again, this is on average. We're not going to measure people's body parts, but on average, if someone was 168 centimeters tall, the length of their forearm and hand put together would be 42 centimeters. So you can see this 0.146 and 0.108. If we go back, actually, we got the figure right here. So if you look on the right center, you can see the upper arm is 0.186. We don't need that because we're just interested in forearm and hand. 0.146 H. So 0.146 times the height of this person will give you the length of their forearm, and 0.108 times the height of this person will give you the length of their hand. Putting them together from their elbow to the tip of their middle finger is going to be about 42.7 centimeters. This is something that you're going to need to do for your analysis. Now, the forearm and hand center of mass. Again, we're not going to chop this person's arm off and then measure where the center of mass is or the mass of their arm. That would be impossible. We use this number up here. So we looked at this figure more recently, but we can see forearm and hand. So this middle row here of text, elbow axis, ulnar, styloid. So the segment weight is 0.022 times their total mass. We don't need to know that yet. And from the proximal side, so from the elbow side moving down, it's 68% basically of the way down. So this is the number we use. We take 0.682 times the length, the total length of the forearm and hand put together, and that gives us the center of mass. So how far down their forearm is the center of mass, and it's 29 centimeters. Again, we'll go over this in class as well, just to we'll work out a problem together so you have a sense for how this goes. So now we have a mass for the subject. We're going to assume that there's 70 kilograms. Looking again at this, 0.022 times their mass is going to give us the mass of their forearm and hand without chopping it off and weighing it. So we we take 70 times 0.022, and then we get 1.5 kilograms for the mass of that segment, and that comes out to be 15.1 newtons, roughly. We're 9.8. What we do is we take the mass times the force of gravity, the acceleration due to gravity, excuse me, and that gives us our force. So we have the force of gravity that is pulling down on the forearm and hand. We also need to look at the load in their hand. So they're holding something, and that force, so the mass is 5 kilograms. We multiply that by 9.8 and we get 49 newtons. So now we have the force of the weight on their hand pulling down, and just the weight of their own arm. So that's something that maybe we don't think about a lot of times, is that if we're just standing there, if you reach your arm out, maybe at first you can't really tell that you're exerting much force to hold it up, but if you hold it long enough, you'll feel it, and you notice and realize that, oh wow, I've got to exert a force to keep this here. So part of the forces is just you keeping the weight of your own arm up. The other part of it is enough force to keep the 5 kilogram weight in your hand up. Okay, now we get into the trigonometry. This is best done in Excel, and we can look at that. You can do it by hand as well. That works. So you can see these. If you look at this stick figure here, there are x and y coordinates at each joint. So at the shoulder, we've got an x of 60.1, y of 124.6. We have all these x and y coordinates for all of these joints. And the key here is that we are trying to calculate moments, which are, if you want to, just think of them as torques. That's exactly what they are. And the torque involves a distance from from the fulcrum, and it involves angles here. And I'll talk about this. So we look at L1, you can see 42.7 centimeters. So that is the length from the elbow to the tip of the middle finger is L1. We found where our center of mass is from the elbow is 29.1 centimeters. So we figured that out as well. If we start at the elbow and we go down 29.1 centimeters, we'll find the center of gravity of the forearm and hand. And then we also found the force. So basically the weight of the forearm and hand. Plus we did find it also for the weight, the 5 kilogram. Let's just say that it's let's not use weight, because I'll just say dumbbell, a 5 kilo dumbbell in their hand, and that one was actually 49 newtons, but the weight of the forearm was 15.1 newtons. Now, we need to use trig to figure out the angle from the elbow. If we were to draw a line parallel to the ground through the elbow, we would create an angle with our elbow. And what we need to do is find, again, because it's a rotational force, it involves an angle. So we have forces, just regular forces, but we're looking for a torque specifically. So that's why we've got to do all this. So we can use the inverse of tangent to find that angle. And here we're using rise over run to find the slope. We do this math, and again, we'll talk about this in class, but we do this math to get 32.4 degrees for this angle. Now, with that angle, we can do some more things. We're looking at forces in the y direction only, and we are able to just with again, so this is not rotational. This is just the forces that we found before. The 49 is the dumbbell, and the 15.1 is the weight of the forearm and hand. And then these external forces, we can do that simple calculation that we talked about before to get the external forces that are holding those up. Now, if we want a moment, though, this is where we've got to use the angles because it's torque and it's a rotational force. So you can see here that, so we're using cosine and for each of these. And if you remember cosine, well, we'll remind you SOHCAHTOA. So it's adjacent over hypotenuse. And so if you look at this angle, this is the elbow, remember? And down here at the bottom of this line is the well, in this case, it's the end of the middle fingertip. The adjacent angle is this line, this horizontal line across the top, and the hypotenuse is the actual forearm and hand, which is what we're interested in here. But we can use cosine and the values that we calculated before, so the angle and this distance times the force, and then the same over here for that. So this one, the 49 newtons, that's for the dumbbell. The dumbbell's all the way at we're assuming at the end of the hand. So this is for the dumbbell. We have to find it for the dumbbell, and then we also have to find it for the forearm and the hand. So there, we've got 29 to the center of gravity for the forearm and hand. We've got 15 newtons for the force, the weight of the forearm and hand. So in the same way, we're finding the external moment, what rotational force is keeping this arm up with this dumbbell, and we find it to be 21.4 Newton meters. Again, we'll walk through this more slowly in class, but this is to give you an idea of how it works. All right. So I hope that was useful, and I'll see you guys in class.